Okay, so hello everybody, and welcome once more to this fourth day of the Escape Summer School. This afternoon we'll have with us Maximilian Noth, and he will be speaking about unit testing and continuous integration. And as always, please don't forget to pull the GitHub repository, as well as to write any kind of questions in the specific Slack channel. So whenever you want, Max, please go ahead. Thank you.
Yes, thank you. Hi, everyone. We are going to talk about unit testing, test-driven development, which is a special form of developing your software using unit tests and continuous integration, which we'll be talking in the end of the session, which is about running your test suite automatically on a server in a reproducible way on many different operating systems if you want, or on many different versions of the software, so you can be sure that your software works on all the intended operating systems. I won't go, I don't want to reintroduce myself again. So if you want to know who I am, I did a short introduction during the Git lecture. You can check out the video from the Git lecture, the first couple of minutes to see who I am. I will just go ahead and start. So we will do a bit of an introduction today into unit testing in general, and I will briefly mention how you would maybe do unit testing in other languages other than Python, and then we just fully concentrate on Python using the pytest framework. This will be, again, this overview is always a bit misleading. We will spend most of our time here in this one pytest section, and then we will briefly cover the topics of test coverage. So how we measure if most parts of our code are actually covered by our unit tests, that we can be sure that all parts of our software are correct. Sometimes you do need to do some mocking or monkey patching if you cannot test the real world system you are supposed to test, or you are supposed to test against. Which is often the case if you are writing software that speaks to a specific kind of hardware, and you don't have that hardware during the testing of the software. For example, if you write software for a complex telescope, you cannot give every developer a complex telescope to run the unit tests. So you need to somehow mock the real thing and have some kind of virtual thing that the developers can use to develop their software. And then very briefly, after we learned how we can do unit tests, we can then learn how we can use this test-driven development, which basically only means that before writing any of your actual code, you will write the unit tests, and you will this will be then your guideline for the actual implementation. So you have your unit tests, and they will all fail because you don't have any code yet, and then you can start writing code and write code until the unit tests are all passing. This is basically the idea of test-driven development. And then this is a bit specific to Python, but it's a very nice extension of this pytest module, which is called doctest, which makes sure that also all the little example snippets you put into your documentation are running correctly. So it basically goes through your documentation, looks where you have code snippets in your documentation, and executes those code snippets and make sure they work, which is a really nice way to guarantee that your documentation does not get outdated and every example you give your users is still working. And then in the end, we will talk about this continuous integration, which again means we are using some kind of web service or server to run our unit tests in a reliable environment, so that we can check for each of the developers independently from their own machines that the code is working as we want it to work. So again, the warning here, if you have not been to the other lecture, there's very many code examples here on these slides. And I would recommend not to try to copy them, because especially for the Python code, you will get not working code from copying these examples from the slides. All the examples you see on these slides are actually in the repository as Python files or as config files, and you can just copy it from there, or you type it by hand. And again, to learn these things, it's probably best that you type it by hand and make sure that it's the same as on the slides. But if you clone the repository, all the code snippets you see on these slides are there as Python files also on the disk. And actually they are just included here into the slides automatically from the files that are really on the disk. Okay, so let's talk about unit testing in general, how you would, why we need it, how you can do it, and then we go into detail about how you do this in Python for Python packages. One of our most important steps in writing software is making sure it actually works. And I mean, we probably all have done this at some point manually. So you write some script, you run it, you see if the output is what you would expect. You look at plots and see if they match your expectation. I don't know. You can think of various methods to manually check if your software is working. You fire up IPython and type in the commands you implemented and see if the answers are what you expect, for example. But this is very tedious. You have to do it over and over again. It is error prone because you might not do it in the exact same way. Many things similar to what we discussed in all these reproducible science lectures. So every time you do something manually, it's very hard to repeat. It's very hard to do it reliably, and it's tedious. So you probably won't do it as often as you would if you could just hit one command and everything runs automatically. And that really brings us to our need for automated tests that test that our software is working as we designed it to, or as we are required to design it if you have some specifications, that the software follows this set of specifications. And this broadly happens in three main categories of tests. There are unit tests, which are testing one specific piece of code, a little function, a class maybe, or methods of a class, the behavior of one class. And you should really make sure that it's only testing this one small piece of code. Then there are integration tests, which basically bring multiple units together and only then test if they can work together. So you made sure that all your little things work, and then you can test that they work together using the integration tests. And we do scientific computing, and in scientific computing, we often have to deal with large data sets or some performance requirements. If we do real-time analysis for our telescopes, we have very strict performance requirements, probably because we need to keep up with all the data that is coming in. So we also probably want to make sure that our software is fast enough to keep up with these specifications. So these would be then performance tests. And all these should be able to be run in an automated manner in a really reliable environment, so that we can easily run them and see the results and just have one command basically to type, and then it reports to us if it was successful or not and where it failed. And most of this lecture will be about unit tests because they are the bedrock of all more complicated tests. And the important thing about unit testing is that they require a modular design of your code base. So if you have just one giant 2,000 line or 10,000 line Python script, which does imperative commands from top to bottom, you basically cannot write unit tests for that. You can just run the script and see if the overall output is correct. And if it is not correct, you basically have no idea which of the 2,000 lines or 10,000 lines of your Python script resulted in the error. Or even harder, if there was no error, but the result is wrong, where did it go wrong? So these put rather strict requirements on that you write small functions, small classes that are well contained, that can be separated into their own modules and that can be tested independently. We want to write unit tests that have the most controllable environment, which only test one single concept or one single small part of our code base, so we can sure that if something breaks, where it broke and what is the problem. And from these unit tests, you can think of them as Lego bricks, right? You want to make sure that all the small bricks are designed properly, that they work together. And then if you build something complicated, you can just rely on the fact that you tested that all the individual pieces work and test how it works together. And this is then the integration tests. And these unit tests must be fast and easy to run. Otherwise, you wouldn't run them, or you wouldn't run them only rarely and not every time you develop something and you forget or right? So really, the most important thing is it needs to be easy and it needs to be automated, which is basically true for anything that needs to be reproducible. If a recipe is a complicated 1,000 step procedure, you have probably more than 1,000 chances to do a step wrong, and then it's really hard. So we need to automate as much as possible always. So we can talk a bit about the 5 most important properties of unit tests. And of course, I mean, you can only talk about properties of something if it exists, if it's existing. So the most important thing is start writing those tests for your software. But then we have these 5 important properties. So we need to make sure that the unit tests are testing the correctness of our code, and that it's really just looking at what the code does and how it behaves in respect to the requirements we have, the specification, what we actually want the code to do. The second thing we need to have for our unit test suite is completeness. So we should have tests for every piece of software we wrote, and that should cover all the use cases of our software. And one really, really major point I want to stress here is the readability, because how do we make sure that there are no errors in our tests? You could now say, yeah, let's write tests for our tests, but where do you stop, right? If you write tests for tests that then need tests, you're in an infinite recursive loop. So tests need to be inspected by the developers and be judged by I to be correct. And for this is it immensely important that the tests are actually readable, straightforward code that can be verified by this inspection step. And good unit tests demonstrate how your project is supposed to be used. So they also simultaneously function as documentation, because you write unit tests for the use cases of your software, which then demonstrate to your users how the software is intended to be used. And especially for scientific code, it's sometimes hard to fulfill the last claim here, the resilience, because, for example, we work a lot with Monte Carlo simulations that use random numbers. So how do we make sure that, for example, if we change the random number generator to a more efficient algorithm, and then some test is breaking because of that, how do we make sure that the test is not breaking because we just switched to a different number generator, but because really something is wrong with the underlying algorithm? And that's sometimes hard to do. Sometimes tests will fail with a false positive, although the code it is supposed to test is fine. So this is what I mean here with resilience. Tests should only fail if the code that it is supposed to test is broken, and not under any other circumstances. Yes, so this is the good properties of unit tests, and we will see more about these examples later in the pytest section. Most of or all modern languages have one or more frameworks for writing these unit tests and executing them using single commands. For Python, we will get to learn pytest. For C++, there are 2 main frameworks I want to mention, which is the Google test framework, which is very commonly used for C++ projects, and there's a new header-only implementation of a unit testing framework, which is called Catch2, which also works very nicely to define these unit tests. Java has now for a long time this JUnit framework, and I think it's now at this 5th or 6th iteration, and this is the standard for unit testing in Java. And when you go to more modern languages, you start to see that unit testing really gets more important and important. So in Rust, for example, a rather new compiled language, unit tests are part of the language itself. So you have built-in functionality to declare and run unit tests. And very similar in Julia, there is a module test in the standard library, which you can choose to declare tests and then run them in a standardized manner. And you don't have to install any additional packages because it's part of the standard library. So just a small note about the integration test. Like I told you before, this is about putting all the single pieces we have already tested with our unit tests together. And this can be, for example, a command line application. So if we wrote our script that does our analysis, we run it and on some data set where we know what should be the result, and then we can compare if the outcome is what we expect. And this should basically only test how we plug the different units together, because that the different units work, we have already established via our unit tests. And of course, with different applications, different analyses, this can grow rather complex and complicated. So these will normally also run much longer than the unit tests, which can be a challenge. So some projects run, for example, very large sets of integration tests only before they make a new release. So not like we would do for the unit test, we don't run it in the CI server for each and every push or pull event, but we only run it just before we make the next release, check if everything is working on these large integration tests. And if it's all working, we can make the release. And if not, we have to patch the errors before we make the next release. Unit and integration tests are mainly about the correctness of the code. So does it give the correct answer for the question you are asking? It usually doesn't really test the performance. So you don't run a timer and check how long the unit test took and then fail if it took too long. So you have to do, for most of our code, at least some basic performance testing and profiling. And I won't go into this here, how you can do this. There is a profiling lecture on next Monday, I think, where it's all about measuring which parts of your code are slow and how you can actually optimize those slow parts then. So we will use the same example I coded in this live demo in the Git lecture, the simple function calculating Fibonacci numbers. And I put this into the GitHub repository. If you look into the Escape School, you will find a testing directory and the Fibonacci directory inside. We can look at this and we will see there is a docs folder and a Fibonacci folder. And there is 3 files we will learn later more about in the packaging lecture what these mean. But for now, you can ignore those and just run pip install -- editable dot, and this will install this Python package into the school environment. So I did this before, but I will do this again here so you can follow along. I will activate the Conda environment for the school, and then I will run pip install -- editable dot. And this means that we install this package into the environment, but when we edit our files here, we will automatically see this and we don't have to reinstall. So this is very handy for development. Okay, that worked. And then we have inside this Fibonacci, we have an init.py, which is the main entry point for Python packages. And here we have, together with some documentation, this example code here. And you can run pytests in this directory just using the pytest command. And it will automatically look for all tests it can find in this directory. And I put these into a tests directory inside this Python module and then in a file called test_fibonacci.py. And we can look at this file. And this is our very simple first test here, the one test we ran. So we import our function from our module and then use the assert statement to make sure that the answer we expect from this Fibonacci function is the one we expect. So assert statements raise an error if this condition here is not true, and that will make our tests fail. So how does this all work? let's talk a bit about how pytest actually does these things. So this is pytest is a standard framework for writing unit tests for Python projects. It is not in the standard library. You have to install it from PyPy or via Conda. There is a unit testing framework in the standard library, but it's rather old and it's much harder to use than pytest. So I would recommend to every one of you to just use pytest and not try to restrict yourself to this unit test module in the standard library. Most of the Python packages nowadays use pytest, and it really is the standard, even though it's not in the standard library. And for all our tests, we will use these. Sorry, we will use these assert statements. And like I said, assert makes sure that a Boolean statement is true, and if it's not true, it will raise an exception. And tests fail for pytest if one of these assertions raises an error, or if any other exception happens during the execution of the test. So you can explicitly have test conditions where you use the assert statement, or you can just test that some code works by not throwing an exception inside the test. And like you saw before, pytest has this automatic detection of test functions. So pytest will look for all modules that start with test underscore or end with underscore test.py. And inside of those modules, it will look for functions that start with test or methods of classes named test that also are starting with test. So basically, the simplest way is to just start writing a file that starts with test underscore and then put one function inside that is named test and something after that. And then you can run the test using this pytest command. And I just for you for later, I put the documentation here into this pytest framework. So let's look at this again. So we have this simple test function here, def test Fibonacci. We import our function inside of this test. We will see later why this is important. And then we make our test. So we test that the 4th Fibonacci number here is 3 and the 7th Fibonacci number is 13. And then we can run it using the pytest command. And I will now go into another directory. So in the slides directory, I have all the examples from the slides. So it's in the school repository, then in the testing directory, slides examples. And I can also here activate the school environment. And then I have this first simple example here in the step 1 directory. So here's a simplified version of this Fibonacci code again. And then there is this test Fibonacci, which is exactly the code we have just seen on the slides. And then we can run pytest here. And we see one green dot here, which means it ran one test. And all the tests have passed in 0.01 seconds, so rather fast. And I can also add the -v option here to get more output. Then I see exactly which tests have ran here. This is now one test that is coming from this file here, and the function name is also shown here. One important thing is you should always make sure if you write tests that they actually fail if your software breaks. So let's break our software here by also returning 0 for the n equals 1 case. So if we now do this, we break our recursion, and this function will now just always return 0. So let's run our pytests again, and we see that it fails. And this is how a failed test looked like. So we can now see that this test Fibonacci test failed, and it shows us where it failed. So the Fibonacci 4 returned 0 instead of the expected 3. So we have an error in our code that resulted in returning the wrong argument here from this Fibonacci function, and our test now complains that this is not correct. So let's change it back to 1. Run the test again, and it passes. this is something you should try out always when you write unit tests. So of course, if you do test-driven development, you don't have any code yet. But if you're writing tests for existing software, write the test and then break the software intentionally to see if your test actually catches the breakage. And like I said, you should import these functions that you are testing inside of your testing function because of this automated discovery of tests. So imagine we break now our module so completely that even importing it fails. And that would result in pytest not even be able to find the tests anymore because the import already raises an error. And this is why we import the code we are testing only in the test function and not at the top of the module. I can show you what happens. So let's edit this. Sorry, wrong monitor. This test Fibonacci so that the import is now at the top. And let's break our Fibonacci.py by making a typo in the function name. So let's say we have a typo in our function name. And then we run pytest. And then we get an error from pytest at this test collection stage. And this is something we really want to avoid. So we have an okay-ish error message here. So it says cannot import Fibonacci from Fibonacci. But imagine you have a very large complicated or very large package with many modules, with many functions. And then the whole test suite fails to collect the tests because one module has a wrong import. So if we move our import inside our test function, the test collection will work, but now the test fails with the import error, and we know exactly which test failed and why, and then we can fix it. So let's go back and fix it. And now the test should be running again. Yes, nice. Okay, so that's just why we are using this strange pattern of not importing at the top, but importing at the top of our test function. So the next thing you might want to do is also make sure that you are testing, for example, invalid input. So what happens if in our simple Fibonacci function, someone is giving us a -1? And let's try this out. So let's add a new test to our testing suite here. Sorry, again, in this example directory. So for you to follow, I'm in this testing slides examples step 1. And now I want to add a test. Still have that open, sorry. I want to add a test. What happens when somebody gives me a -1? And I will call this test invalid input. And again, I import my function. And now let's see what happens if I do Fibonacci of -1. Okay, so this looks really, really strange. Basically, we get an infinite recursion here. And at some point, Python saves us. It's realizing that we tried to recurse for over 900 times now, and it stops us basically. We have the maximum recursion depth exceeded. And this is, of course, not an error you want your users to see if you do something like this. So what we actually want to do is if somebody gives us invalid input, like if n is smaller than 0, we raise a nice error message. So we could say something like n must be larger than 0, but we, or larger equals 0, got this. So let's run our test again. And now this test still fails, but it shows us this nice error message. So the value of n must be larger or equal than 0. It got -1. But this is actually now not an error. This test shouldn't fail. It's what we expect. So we need a way to test that we can actually make sure exceptions are raised when we expect exceptions to be raised. And pytest offers a very nice function for this. So we can import pytest here. And then we check that a value error is really raised by this code by using this this context manager. And now the test will fail if this code here in this context manager does not raise this kind of exception. And we could even make sure that the message is what we expect, but I won't show this. And now our tests are passing. So let's look again. We run 2 tests, Fibonacci and test invalid input, and both are passing. If I now change the code and say, for example, if n is smaller than 0, return -1. This test again fails because it did not raise the error. It just returned some invalid value, which is not what you would do in Python. So in Python, if you encounter an error condition, you raise an error. So this is the nicer API for people to use. So we'll do the first thing and test that it actually is raising an exception when you run this code. And just a note here, you can do the same with pytest.warns if you want to make sure that some piece of code emits a warning to your users. And we are all writing scientific code. This is a data science school, so we have to live with some strange edge cases. For example, we are all using, if we want to do scientific computations, these IEEE floating point numbers, and these have limited precision. And one of the most well-known example of this is that if you add 0.1 to 0.2, the result is not equal to 0.3. And that's surprising to many people when they start doing computer programming, why this assertion here will fail. And the reason is that we cannot store exactly the numbers 0.2 and 0.1 and 0.2. Or we can store 0.2 exactly, I think, but not 0.1. And 0.1 is then rounded to the next representable number on our computer. And it just so happens that if you add the closest number to 0.1 to the closest number of 0.2, this is not the closest machine number to 0.3. And if we explicitly type 0.3, we will get the closest number that is representable, that is the closest to 0.3. The correct way to handle this is that most unit testing frameworks have methods to do this kind of floating point comparison. So in pytest, we can use pytest.approx. So we only want to make sure that this equation here holds to the level of floating point precision. And you can read more about these floating point precision issues on this very funny URL here, which is the 64-bit representation of 0.1 plus 0.2, which is this 0.3000 many zeros and then a 4, which is exactly the reason why this comparison here fails. I have also an example for this. So if we go back to this directory and now enter this basic example directory, I have this floating point directory here, and we can just run all the tests in this floating point directory. If we give this to pytest, and again at the -v option to get some more detailed output. So this test here is basically the one we were just looking at, and it fails. And if you do this minus v, you will also directly see why it failed. So somehow, for some reason, 0.1 plus 0.2 is not exactly 0.3, but it's 0.3, many zeros, and then a 4. And the test with the pytest.approx is passing. This works nice for Python floats and for Python single numbers, but we also often have to deal with large NumPy arrays and with many numbers at the same time. And thankfully, NumPy has also testing functionality to help us compare many values at the same time. So we can now have this array of x values and can test that, for example, if we apply the NumPy sign to it, we get the expected values. So we use this numpy.testing.assert array is almost equal. And we can specify to how many digits we need the two arrays to match. So here we require a precision of 15 decimal digits between the result of our function call here and the expected results we give it as a second argument. And another very helpful function is assert all close, which works very similarly, but you don't give it the decimal precision, but you can give it a relative tolerance and an absolute tolerance, how far the values are allowed to differ between the two arguments you give it. So we can return here our define a polynomial function here, can give it some input and test that it is what we really expect the values to be using this assert all close mechanism. AstroPy has very nice support for units. We will learn more about this in the AstroPy lecture. But you might then also want to, or you will need to test your unit-based code. And there's also some really nice methods in this AstroPy units package to do that. So for example, here we define a speed in meters per second and a distance in kilometers. And then we can make sure that if we divide the distance by the speed, we get a timeout or get the correct timeout in seconds here. And even if this is using kilometers per second and meters, kilometers and meters per second, AstroPy will, before comparing the values, transform all the values into the same units and then make sure that these are actually close with respect to the floating point precision. And this is close works on one single value, and then there's all close, which is very similar to the NumPy all close, but it supports units. So we assert that all of these results are close. And this is basically what you need to know to write basic unit tests for your software. You call your functions, you create simple test functions that call the function with a specific input and make sure that what it returns is a specific output you expect. Sometimes our testing code needs access to additional data, and sometimes many test functions can work on the same input data. And pytest has a method for this called fixtures, which lets you inject your test data into the different unit tests. And this works using a decorator, so you can have a function that returns your data. And in this example, it's just a Python list with 3 elements. And then you can decorate this function with pytest.fixture. And you have to define the scope that it's using. And scope here means basically if you have many tests using the same fixture, will it create the data for each test individually, or will the same piece of data be used for each of the tests? So if you do scope equals session, that basically means this fixture will be the same for each time you call pytest. If you say this scope is function, each of these tests will get their own copy of this fixture. So for example, if you would change the list in this first test, the second test would now also see the change. And if you now change this to scope function, the second test wouldn't be affected by the first test changing the list, because the second test gets a fresh copy of the list when it runs. And you can just give the name of the function here as argument, and then inside this function, you will get the return value of this fixture. And the many useful fixtures that pytest provides out of the box are listed in the documentation. I will go over 4 of the most important ones. So if you are, for example, testing input or output functionality, you will want to use the temporary path methods of pytest so that you don't clutter your local development directory, and that if you run the test multiple times, you don't have the files from earlier iterations still lying around and interfering with your current test. And this is what these temp paths and temp path factory fixtures are for. Then you might have also code that is supposed to print something. So you want to have a program that tells the user something. You can just imagine this simple hello world program. And then you want to make sure that that print actually happened. And for this, you can test if there was output to standard out or standard error using this capsys fixture. And the same goes for logging. So Python in the standard library has a logging module, which is really good to enable more complex logging output from your applications and libraries. And then you can also use pytest to make sure that a function that has to log something really did that. And we talked a bit about monkey patching in the beginning. There's a decorator that allows you basically to modify Python code that you are using for your test, and then it will revert those changes after the test so you don't interfere with something else. So let's first talk about this capsys fixture. So we have a function here called greet, and that takes a name, and then it should print to the standard output the standard greeting, hello world or hello escape school 2021. And we can require this capsys fixture here, and then we call our function, and then we can make sure that this function actually printed what we expect to the standard output. In we ask this capsys fixture for what was in the standard out and standard error. So we read what was written before, and we get this in a variable called captured. And this captured variable has standard out or an out and an error attribute. And in this case, we want to make sure that what was printed to the standard output stream was the message we expect here. So we want that this test is actually, or this code is actually producing hello, and then what we gave it, and this is tested here. And we can also run this example in our example folder here. So this is the fixtures example, and then the test capsys. And this also works. I mean, let's look at this again. Fixtures test capsys. So this is basically the same as on the slides, and you see that it works like we expected. And again, we can try to break it. So if we forget, for example, the comma here, we run it again, this test fails, and it gives us a nice assertion error here that really shows the difference between what we expected and what we had. So we can immediately see that here is the comma is missing. And then we can fix our code again. Rerun the test, and it works. Very similar for the logging example. So I have a function here that should do some work, and while it's doing this work, it should also report using this logging module what it's currently doing. So we get our logger, we log with the level of info that we are currently doing some work, and then we log that we are done when we are finished. And then we can use this cap log fixture to catch all the logging messages that are above this info level, and then we can make sure in the test that we actually captured 2 logging messages, and that each of these logging messages had the level info. We could also, again, test the actual logging message here in when we would check something like record.message, and all other metadata that logging attaches to these log records are also available to us to test that the logging is really happening like we intended to do. Yes, and one of the most interesting things I think is this temporary path fixtures, which give you a temporary path for each individual test you are doing, and that sticks around after the test is done. So if you are implementing some I/O functionality, and we will see an example for this now, you can make sure that the test is writing the file correctly, and if it fails, you will still have access to this directory, and you can inspect the files there and see what is going on and why it failed. And then there is this temp path factory, where when you need a fixture, a temporary path for more than one test, you want to test several things together in the same directory, you can create temporary paths that have a different scope than the default function scope. So again, AstroPy comes tomorrow, but I use this because AstroPy is quite nice for reading and writing data similar to pandas. Data frames, we have this table here, and we write it to a CSV file, and then we read it back again and check that the values are all the same between the version we wrote and the version we have read back from the file. And this will run at least on Linux in your temporary directory path, and then it will create a pytest of your username directory and the current pytest session and the test2CSV current. So this is called test2CSV. So the directory, the temporary directory, is called test2CSV current. And this is only a symbolic link. It will actually add numbers, and each time you rerun the test, the number is increased, and the current links to the current last iteration of the test. And this is something I want to show you again here in this example folder. So we have the fixtures example and the test temp path. And this is just the example from the slides. But let's run this first and then break it again. So this is in fixtures and test temp path. And if it just works out, we don't see any special anything special. We just see the green dot. But if we break this now, for example, yeah, let's just change the file name so it doesn't actually find the file when it tries to read it back into our program here, and we run it. Then we get a large error message from the table. This test has failed, and it shows to us here above, where the test failure is reported, which value this fixture had, so we can check. And this is now this path on my system. So currently this is pytest of Max Nö, pytest 2, because I ran this test before. And then it's the first iteration during this test suite of this test function. So let's inspect this directory. And then I can immediately see that this file name is not what is what I expected, and this is probably why the test has failed. And I could also use my editor to actually look at the file test, and then I see that the file is fine itself. It all worked out, but the name is wrong. And then I can fix the name again and run it again. And it's all working again. One thing I won't show here, but which is also relatively common. So many times you need a cleanup step after you created the fixture. So you need to acquire some resource. You want to use it in the tests, but after that you need to somehow clean it up. And you can do this using a generator function in pytest. So here I took the example of a database connection, which I have to close after I used it in the tests, and I have to write a generator function here that yields the connection. And what this will do is that pytest will run this function until it yields a result. Then it will use that as input for the test. And after the test has finished, the rest of the code after this yield statement will run and perform my cleanup. And if your resource provides a context manager, this is even better, because then you can just yield inside the context manager. So you connect to your database and use the context manager to do this. And then you can yield this connection. The test runs inside this with statement. And when the test is finished, the with statement exits and closes your connection to the database or cleans up your file, or whatever you can think of that needs a cleanup step. This is really, really useful if you have these cleanups to do after you acquired some resource for your tests. And in the beginning, we saw that we had to write all our assertions by hand for all the Fibonacci numbers. And because we are lazy, we only put in 2. So we only tested 3 and 7. And what I did here, I took external reference. I really went to Wikipedia and just copied the list from Wikipedia and inserted it into my Python script here. And then I can use this parametrize and say, okay, I have my ends I want to test. I have the true answers I just copy from my specification, in this case, the Wikipedia article on Fibonacci numbers. And then I put them in as input for this test. So I use this mark parametrize function of pytest, give it 2 arguments, the n and the expected, and have to use this zip to make sure that I get for each of this each iteration of the test, then basically the combination of 1 n and 1 number, Fibonacci number. And then I can define this function here that takes these 2 arguments. And then I can just write n equals Fibonacci of n equals the expected number. And I have a test that runs for all these numbers here, but I had only to write it once. And because of this parametrization, it will run for all the test cases. And pytest also has a very nice way of reporting this. So if we go back to these examples, and this is, I think, in the step 3, pytest -v, you will see that it basically has 1 line for each of the parameterized tests and reports which values were inserted. So n is 0, the expected output is 0, n is 8, the expected output is 21. And again, we can just test if this is really working as intended. So if we break some special case here, if n equals 8 because we are evil, we return again -1. We see that only this specific test is failing, and we get a nice report that this exact test is failing, although we just have 1 generic test function here. So this really helps you to deduplicate your code, to test many different cases, scenarios, and the most common version is to have 2 lists of expected inputs and expected outputs, and then use that as parameterization for your function and test that all these cases work. Some more advanced topics are that you maybe write a package that has lots of features, and some of your users only need some of the functionality, so you make some of the features optional. And then you can specify that tests should only run if your optional dependencies are available. So if you have, for example, a package that only needs NumPy for some parts of it and says that this is an optional dependency, you can skip all the tests that need NumPy when someone doesn't have NumPy installed. So this is what this pytest import or skip does. If you don't have NumPy installed, this test will not be executed. And another example for these are platform-specific code pieces. So this, for example, this test here would only run on Windows. So we skip this test if this.platform is not Win32, which is Python's way of telling us on which platform we are, and Win32 is any Windows system here. And we can also give a reason that is reported to someone on Linux or Mac OS that this test was skipped because they are not on a Windows system. Let's see how this works out. So I'm now in the school environment. So I have NumPy here installed, so this test should run. Pytest, and I think it's the test skipped. Yes, so we see one test ran and one test was skipped. If we add the -v flag, we should get more output. So the NumPy test was executed and it passed, but the Windows test was not executed because I'm currently on Linux. I could now, for example, deactivate my school environment and create a new virtual environment. And in this virtual environment, I don't have anything installed yet, so the first test should also be skipped. And this will fail. Okay, sorry. I need to install pytest in this virtual environment. I need pytest to run the tests. And now this test should fail, or should be skipped. Yes, exactly. So I'm now in an environment where I don't have NumPy anymore, and this test is now skipped because we couldn't import NumPy. But our test suite didn't fail. So this is just skipped, and tests that are skipped don't make the test suite fail. Okay, let's go back into the school environment. And then the NumPy test should run again. Okay, I'm not switching to Windows to show you that the Windows test is actually executed on Windows. You have to try that yourself if you're on Windows. Sometimes occurring case is that you write tests that you expect to fail. So one of the examples would be our testing case here for the floating point numbers, right? This is just a demonstration where we know that this test of for the reasons of these floating point precision issues will always fail. But the real world scenarios are basically you wrote tests for functionality that are, for example, in the specification, but are not yet planned or implemented in the short term. So you write down the tests to have them and to give someone the possibility to implement them, implement the functionality you are trying to implement. But because you run continuous integration, you of course don't want for tests that are supposed to test future functionality that this results in all your unit test suite saying that there is an issue. So you can just mark tests as xfail, which stands for expected to fail. Yes, so here the stupid example is we assert that pi equals 3, and then we can remove this xfail if we ever declare pi exactly equal to 3. But this will probably take a long time. So we, in the meantime, we just declared xfail. And we can do this also now for our floating point example. Test floating. So this is the naive code, and then we add a pytest.mark xfail. And if we now run this test, this is not reported as an error anymore, but as xfail, and we get overall our test suite passes, but we got one xfailed test. And if you work on larger projects, it's very handy to be selective with what tests you are running. So if you work on this really large project and you just change one little part of the code, you probably first want to just run the tests that are testing this part of the code. And only when you are done with your work, you will run the whole test suite to make sure you didn't break anything else by editing this part of the code base. And pytest has very nice methods to select what tests are actually run. You can just select one single test by giving it the fully qualified path. So you give it the actual file where the test is defined, and then you can use this double colon notation to tell pytest which test function inside this file should be executed. And what is really, really handy if, for example, you implemented something new or you are investigating a bug, you can just rerun the test that failed the last time you ran pytest. So let's say you have 500 tests. You implemented something that broke 2 of them. You don't want to rerun all the 500 tests every time you try to fix this. You just rerun those 2 last failed tests until they pass. And then you, of course, need to rerun the whole test suite again, because with your fixes, you could have broken something else. So you run the whole test suite after you made sure that the tests you are interested in pass again. And sometimes it also doesn't make sense to continue testing when the first error occurs, or you want to minimize the number of errors and then don't run the remaining tests. So you can tell pytest to stop the unit test suite after 2 or 1 or 10 tests have failed. And then there's more fancy stuff. So you can also use matching expressions. For example, we can only run the tests that have fib in them. So if you do this here, pytest minus k fib, it will do this test discovery and then go through all the tests. And if you add the -v option, we see each test that is run. And these are all the tests that have fib somewhere in their name. So for example, this file is called test Fibonacci, so it's run although the test function itself does not have the fib. And then all the other fib functions are also done. And I can even invert this, so I can say to pytest, please run all the tests that do not have fib in them. And what is really easy, if you don't, really nice to have when you have installed a package and are investigating some strange issue with another package that's not yours, you can actually, if that package is using pytest and installs also its test suite, you can run actually the pytest test suite of that package using this pyargs argument. So remember, we installed this Fibonacci package somewhere some time ago in our environment, and I'm now in a completely different directory in my home. And I can now ask pytest to please run the test suite of the Fibonacci package. And that is exactly the test we saw in this demonstration. And then we talked about these integration tests and that sometimes these are quite slow to run, and you maybe don't want them to run all the time. And for these, you can define custom markers for tests in your test suite. And you can do this in this pyproject.toml configuration file, which is something we will hear more about in the next lecture about Python packaging. But basically, you declare a marker, which can be called integration or slow or whatever you can think of. And then you can mark single tests with this marker. So if I mark this test as slow because it just sleeps 2 seconds, I can then use the -m switch again to select tests that don't have this marker or that have this marker. So pytest -m slow would only run the slow tests, and pytest -m not slow would only run the not slow tests. And I think Carl will go into this in more detail, but in the debugging session on Monday, I will not show you this here because Carl will do this, probably show you the Python debugger and the IPython debugger. But you can actually, when a test fail, ask pytest to immediately put you into the Python debugger. And this is really handy because then you can really investigate why the test has failed, and you can go to the cause of the bug very quickly using the debugging tools, again, which we will introduce on Monday. And I forgot to comment on this. So this is how you enter the debugger, but I wanted to stress how important tests can be for actually solving a bug and debugging. So if some user of you or yourself, you encounter a bug which is not tested yet, write the test first. Think of a minimal example that triggers this bug, and then write a test that fails because of the bug. Because this is now extremely helpful to actually finding and fixing the bug, because you can, when you make changes, run the test suite and run it and make changes to your code base and rerun the test. And when it then passes, you can be sure that you actually fixed the bug and didn't introduce any new ones, because all the other tests are also running. And then we go to the test coverage, which is about the completeness of your test code. So there are different definitions of coverage, but the easiest to understand is the so-called line coverage, where the program in the background basically just counts the number of lines that were executed during the tests and the total number of lines of code, and then divides it, and you get a percentage of lines that were executed during the tests. And this can be very helpful to find sections where you didn't yet write enough unit tests. So if you're in a historical code base that doesn't have any tests yet, you will have 0 for all the files in this package, and then you start unit testing. You write the first tests, and you will see the coverage increase in the different sections of the code, and then you can use it to choose where to focus next, where you have to write the next unit tests to get to a good coverage of this. And this also very useful in this continuous integration systems. You get these badges. The code coverage is 90%, or these changes are only covered to 10% by unit tests. So this is helpful for code review. If your automated coverage system tells you this pull request does not have enough tests, you can immediately say, yeah, please write some more unit tests for the code you changed, and then we can come back to the code review. To run this using pytest, you can just add the --conf argument, and then it will run the coverage report or create the coverage report for the given module. And there are different formats which you can use to generate this coverage report. So if you don't give anything, it will just print some numbers to the command line. And if you export it as an HTML file, you can look at it in the browser using this handy command down here. And for example, these automated CI systems, they usually want the coverage report in XML, and then you can upload this XML coverage report from the CI system to the system that provides you these reports during the code review. So let's see how this works out for our module here. I will go back into this Fibonacci directory here, where we just have this simple unit test. So in the Fibonacci directory, there's this test directory and test Fibonacci. And we just test the 0 and the 1 Fibonacci number. And if we now do pytest --conf equals Fibonacci, we get our coverage report here. And unsurprisingly, the test file itself has 100% coverage, of course, because it's basically the code that is run during the tests. But we see that only 75% of the lines in our actual code base are executed. And we can get more detail if we use this HTML coverage report. And then it says it has written our coverage report to HTML-conf, and then we can use our web server from the standard library of Python to serve this directory and to look at it using our browser. It will display the URL here. You can just open this. And then you get this, this nice view here where you can click into the different files, and then it marks in red for you the parts of code that were never executed. So we have 2 lines that were never executed during the tests. We didn't test for our invalid input, and we didn't test for higher numbers of the Fibonacci numbers here in this instance of our example. So let's copy some of the examples. Slides, examples, step 3, I think, has this parameterized tests, and I will move them into the Fibonacci test directory. And if I now execute this again, I have many more tests here. And I opened the coverage report again. Where's my browser? Sorry. Here. I update the page, and now this red line here is gone because we added more tests. But this one is still missing. So let's again add a new test here. So let's also test for this invalid input. Same example as before. If we enter -1, we want to make sure that we raise this value error. And then we run the test suite again, export this HTML coverage report again, and now we should have 100% coverage. Yes. Okay, so we have now 100% coverage in this Fibonacci.py, and yeah, all the lines were executed during the test. So let's talk a bit about limitations of this kind of coverage. So I have some very artificial example here, but imagine we have a condition that is only sometimes true and sometimes it's false. And then we do some stuff only if this condition is true, and we do some other stuff afterwards. So what happens if during the tests this condition is never false? Then we have 100% coverage because we executed all these 3 lines. But actually we didn't test the important case maybe of not doing stuff when the condition is false. And this brings us to something called branch coverage. A similar example is when we call some complicated function from another module with some input data. So here's SciPy optimize minimize with the likelihood function and some data. And this can basically have arbitrarily many branches. Everything can happen. You can get an exception. You can get the wrong result. You can get into all kinds of trouble if you have an error in your likelihood definition or some strange data. So you have to really think hard about if 100% coverage is really 100% of the actual use cases you have. Probably not. And what you can at least do is enable this line coverage. So you can do this branch coverage. So you can add --conf -branch, and then it will also make sure that if you have some if statements, it basically counts it as 2 statements for the condition is true and the condition is false, and it will check if both cases were executed during the test. And if we do that for our case here, I think we will also have 100% branch coverage, but we will see the report about this branching. Okay, so it now has also numbers about our branches. So we have 8 statements inside our file, and we have 6 different branches inside there, but all were executed during the test suite, and all lines are green. And for example, if we have statements that were never executed or were always executed, but could be not executed because of some condition, pytest would mark those in yellow as partially executed branches during the tests. Okay, so very short example about monkey patching or mocking, because I think this is a very specific topic, and if you know you need this, you probably have to figure out a way to do this, which is very specific to your use case. And I'm also of the opinion that extensive use of mocking during a unit test suite probably means that your code is not structured well, because you cannot test all the pieces individually like you would like to. Yeah, but that out of the way, one common case where you will need this mocking. Sorry, my camera went out. I will just keep on talking. So sometimes you have code that talks to hardware, and you want to be able to develop this code and run the test, although you don't have access to that hardware. So you have to somehow simulate this, and this is called mocking. Mocking means you simulate something that is not the real thing you are using for your test, but you have to make some dummy to be able to run the rest of the code and see if it works correctly. And I have one example how you can do this using monkey patching. So monkey patching means, yeah, basically you change the behavior of some third-party code so you can run your test under all circumstances, for example. So here I have a function that talks to an internet server and wants to know if it's healthy. So it makes a web request using the request library to check if it's still healthy. It checks if the result was successful, and then it returns if the server was healthy, passing the JSON payload. So not too important. The important part is down here. So we can use this monkey patch fixture provided by pytest to make this work also without internet connection, or irrespective of what the current status of the real website is. So if we want to report that our isServerHealthy function fails when the healthy attribute here is false or is true, but don't want to depend on the actual current status of our web server, we can monkey patch this requests object to always return something with known content. So here we change the requests get method to always return something where we know what's inside, and then we can assert that our server is currently healthy. And we could do the same thing with a false statement here in the JSON data. And then we could assert that our isServerHealthy function reports false if the data in the request is false. Okay, so for the last couple of minutes, I will very briefly talk about test-driven development, and then we will look into an example how you can do continuous integration. So test-driven development is mainly a paradigm, a programming paradigm, and it boils down to writing the tests first. So if you take anything away for test-driven development, it means writing the test first. In more detail, it means you write the tests before you write any implementation code, and then you run the tests. And because you didn't write any code that actually tries to do what you are testing, they should all fail. And then you start writing the actual implementation with the minimal implementation necessary to make the tests pass. And when all the tests are passing, you are basically done with the initial implementation. But then you can use this to clean up, refactor your code until it is in a situation where you really like it. And during this cleanup and refactoring step, the tests, of course, can be used to make sure that the code is still working and you are refactoring without breaking it. And this is very, very powerful because test-driven development forces you to think about your code before you write it. So you make considerations about the API of your code. You will think about really how your code will be used. And this usually leads to better code because you really put in thought into how it should look like, how it will behave, and how it should be used. And usually this doesn't even slow you down that much, because if you are thinking about the code that much in front, you will have a much easier time to actually implement the code together with the tests you have already written. And this is especially useful when you have clear specifications. So you can just start from a specification document and write the test. So they make sure that any code you will write actually meets the specifications. For example, I I happen to implement some reader functionality for file formats, so I can have the documentation of the file format open to write my tests and see that without having written the reader, I can make sure that the answers the function should create are in line with the documentation for the file format. Also, like I mentioned, when you are investigating a bug or trying to fix it, write the test that triggers the bug first. This is a minimal example reproducing the issue. Boil it down to really the minimum amount of code that is affected by the bug, and then you can start trying to fix it and see that the test is passing. And this is obviously the easiest when you're just starting a new project where you don't have any historical ballast. On the opposite side, it can be very hard to use this test-driven development workflow when you are working in a large historic code base without good test coverage, because it's hard to get started and to set up the infrastructure for this kind of development. And also, if you really don't know where you are going and you're just trying some stuff out and want to do explorative work, test-driven development is also a bit limited in what it can do in that case. Okay, very short example on doctests. So what we have here is our function from our Fibonacci module, and we tell our users how to use it. So we calculate the nth Fibonacci number. This is documentation. And then we have this code block here. So we have examples in our documentation. And then we have these 3 angular brackets, from the Python interpreter. And this basically tells pytest now that this is an example, how our code should be used. And then we even have the result here. And what this does is it looks basically like what you would have in the Python interpreter if somebody manually types that in. And this is exactly what pytest does. If you give it this doctest options, it finds snippets like this in your doc strings and your documentation files and runs them. So again, in this Fibonacci project, I have this doc string here. And I also added a docs directory with this simple documentation page. And there's also this restructured text code block here that shows a usage example of our Fibonacci module. And then I can call pytest with the --doctest modules option, which will look into our actual code, into these doc strings, and with the doctest glob option, which will look for these documentation files which have an extension of .rst. And then you will see that it ran one test also in this documentation file, which is not even a Python file, and one test here in the init, which is our doc string, and then also our normal test suite in this test functions. And we can also break this kind of test here. So in this case, we don't break the implementation, but we break the expectation here and run the doc tests. And then it says, okay, one doc test has failed. This is from the Fibonacci function. And we expected the output 12, but we got the output 13. So we would learn that our example here is broken and we could fix it. Okay, so I'm a bit short on time. Maybe we can have 5 minutes more for the questions in the end to go into this continuous integration stuff. And like we mentioned now many times, a CI system is basically a server that gives you computing power to run your build and unit tests and do code quality checks. And continuous integration means that you run this every time you change some code in a pull request or directly if you are working not using the GitHub workflow on your development branches. And every time you push or open a new pull request, the CI system will start to build your software, run the tests, and so on. And there are many tools that you can integrate in such continuous integration environments and many providers for these kinds of services. And we will see some of them in this lecture. So Yeah, we will go through some of this, and it's basically all about automatization and having multiple configurations for the testing environment, so your developers don't have to test everything using 3 different operating systems and 5 different versions of Python. So there are 2, 3 main providers of CI systems, and many more you can also use. GitHub has an integrated environment since a couple of years, which is free for all GitHub repositories that are public, which is called GitHub Actions and is very well integrated with GitHub itself. It provides Linux, Mac, and Windows builds. So you can add a configuration file and say, I want this test to run on Linux, this test on Mac, and this test on Windows. And if you have private repositories, you can either pay for GitHub to let you use the GitHub Action system, or you can also deploy your own custom runner for these CI systems on your own computers and then use that to run the CI tests using GitHub Actions for your private repositories. And I would really recommend to you, if you have a repository on GitHub, to first try out GitHub Actions, because it's a really nice system. It's well integrated with GitHub, and it's for free for public repositories. The same story is basically for GitHub. They also GitLab, sorry, they also have their own CI system. It's a bit more limited because you only get 400 minutes of build time per month for free. You can request free build time if you are an open source project or in academia. But you can also, like for GitHub, can also deploy your own runner systems on your own hardware. And this is also true if you don't use GitLab at gitlab.com, but you use GitLab in your own environment, self-hosted. Then you can also set up these GitLab CI runners, which can then run your CI jobs inside your own GitLab. And Jenkins is a very widely used platform for self-hosting CI systems. I have not worked with it much. I found it a bit clunky to get started with. So if you are not in the situation where you need a CI system for something else than GitLab or GitHub, I wouldn't recommend it too much. For GitHub and GitLab, just use the provided solutions by GitHub and by GitLab themselves. And there are many more providers for these CI services, which can also be integrated with GitHub Actions and GitLab. And I put some links down here. So if you're not happy with GitLab Actions or GitLab CI, try out one of these providers down here. And these work basically all very, very similar. You have to write some configuration file that defines the steps of your workflow. And unfortunately, there is no common standard. Each of these CI providers has their own formats and rules for how these configuration files will look, and they offer slightly different features, but basically everything in the end has to do the same tasks. So you have to define the environment, the operating systems and software versions you want to use. You want to get your code, you want to install your dependencies, you compile, build, and install your software, you run the unit tests, and then you might also want to upload results or update build package to PyPy, which we'll see in the next lecture on Python packaging. And this is all what a CI system can do. So basically, a CI system is a computer, a server that runs a task you can specify in a configuration file. And these are very, very flexible. They can do very many things. And we commonly use them to run our builds and unit tests. So I've created this demonstration project here, where we can look at this in detail. So this is basically the same code again. We have this Fibonacci module here with the unit tests. And we have these package structure you will learn about in the next lecture. And I have set up this CI system. So I can go to the GitHub Actions tab here. And there's all the CI runs, and some that have failed and some that were successful. And let's look into this configuration file. So for GitHub Actions, you have to put a .github directory in your repository and a workflows directory, and there you can have many different workflows defined. I have only defined a single one here to run the unit tests. So these are all YAML files, which is a data commonly used configuration data file format. And here I can specify how exactly this should work. So I give it a name and I say it has to run on each push and pull request. And then I can define what actually happens. So I have this build job here. It runs only on Ubuntu. I could also say it should run on a specific version of Ubuntu or macOS or Windows. But then I use many versions of Python. So I want to make sure that my package works on all these versions of Python, but I only test on Ubuntu for now. And then the steps are basically what I lined out. So there is this, basically it's a plugin mechanism. So I can define that I want to use this checkout action here, which basically just clones my repository. Then I can use this setup Python action that will install Python for me at the specific version I can define here. And then I can just give commands that should be run. So I have one step here that just updates pip. So I'm sure that I have the most recent version. And then I can run the build steps, which we will learn about more in the next lecture. And finally, I do the real test. So here's the test that my package follows the Python style guide and that it does not have simple syntactic errors using this Flake 8 tool. And here is the full call to the pytest function with the coverage, XML coverage report, the branch coverage, and the doctest modules. And then I use this code_cuff action, which actually takes this XML coverage report and creates basically code review from that coverage report. I have also a pull request open here. I closed it some time ago because it was merged, but we can look at how this works in action. So I have made changes here. So I added this Fibonacci generator function, and then there's also a test for that. And then we can look at this report here. So this is from this code coverage report. And then it tells me, okay, so the diff coverage is 90%. So 90% of my code is covered. And it cannot report the difference to the main branch because I never ran this on the main branch. Sorry for that. But we can also look at the execution of the CI system here for Python 3.6, for example. So you see here all the different Python versions that are tested. And then we can, for example, look at the pytest output here. So this is exactly the same as you would see it on your local terminal, really just a computer running somewhere else, running your pytest test suite and saying that it was successful because all of the tests have passed. Okay, just as some links, I put some useful tools here you can use in the CI system. So code_cuff is about reporting the test coverage. Review NB is a tool I also mentioned in the Git talk for making code review for notebooks easier. And Codesi is a tool that can run the static code analysis. For example, it can highlight in the pull request on GitHub if something is not following the style guide you want to follow for your project. So let's try if I can switch on my camera again. And then we should switch to the questions if there are any in the Slack channel.
Okay, so thanks a lot, Max, for this nice presentation. There was a last question in the last moment, but I mean, there were not questions during your talk. So I would say that congratulations, because I think it was very nice explained and we could all follow up very nicely. There's a question, but okay, we can answer it later.
There's one one question about the coverage. So I think the question is if the branch coverage basically makes a test fail if not every branch is executed, and this is not true. So it will just report a percentage of the executed branches. So it will not make your tests fail, but just report that not every branch in your code base was executed.
Okay. Perfect. Thanks, Max. So we'll stop here for a coffee break. We'll return with the next session again by Max on packaging at 4 o'clock. So in 35 minutes, and see you in the other town. Okay. Thank you very much, and see you now.